In a previous video, I showed you that the position of a jerk minimizing trajectory is given by a quintic polynomial. In this video, I'm going to present a quick and non-rigorous walkthrough of how we find the 6 coefficients that describe this polynomial. It is not essential that you remember the details of this, but you might find it interesting. First, we differentiate the equations of the position in order to get the equations for the velocity. And then, we differentiate it again in order to get the equation for the acceleration. Now, we could just plug in our 6 boundary conditions to get the 6 equations, but first we're going to do something that will make our life a little bit easier. We're going to set the initial time as 0, and when we do that, we find this, which means that 3 of our unknowns don't need to be identified anymore, which reduces the problem from 6 unknowns to 3. And it simplifies those 3 trajectories by removing 3 of the unknowns here. We can gather the known terms into functions of the start boundary conditions to make it look like a bit cleaner. These C1, C2, and C3 terms are functions of the initial conditions. What remains is that we only have to identify 3 parameters that depend only on our end boundary condition. And those equations look like this. And we know the final position, velocity, and acceleration at time tf, since those are all the quantities that we picked. Since we know them, a more useful way to think of these equations is like this, where I have deliberately separated the known quantities from the unknown variables that we wish to determine. And this is starting to look like a very solvable system of 3 equations. The best way to solve this is with a matrix that looks like this. And this problem can be solved by inverting this matrix using any matrix mathematical library, which we will do later.